Hello, everyone. Today we'll be presenting a way to identify properties of neural networks using the technique of interpolation. We will present this in three parts, and I will start with the first one. So the problem that we tackle in this work is to identify a convex region or a union of convex regions such that each point in that region satisfies some property which is given on some desirable property on the outputs. So a neural network consists of several layers. Each layer of neurons feeds into the next one, and each neuron computes as follows. It first takes in the weighted sum of the inputs and then applies a certain activation function to it. So the activation function that we consider in this work is a rectified linear unit, or the ReLU activation function. This takes a max of the weighted sum with 0. We say that a neuron is on if for a particular input, uh, its output is greater than 0. Otherwise, we say that it's off. So to define the convex regions we use, I'll do the following. Suppose we label each neuron in the network with on or off. So on basically means that this is producing a non-zero output, and off means this is producing a 0 output. So note that the neurons which are off do not participate or do not affect the result of the neural network at all. In fact, we have the property that given these labels, each neuron's output is a linear function of its input. An activation pattern is a labeling of neurons such that each neuron is either labeled as on or off or a don't care. We place don't care for neurons for which we do not enforce any constraint on their status. But the invariant we maintain is that every don't care neuron only feeds into either don't care neurons or into the final output to which we are not placing any constraint anyways right now. So the set of inputs that satisfy a particular labeling can be identified as follows. So for each neuron which is labeled as on, we place the constraint that the output of this neuron is positive. And for each neuron that is off, we place the constraint that the output is 0. This set is a convex set because, in short, because we have the property that if every neuron is either labeled as on or off, then the output of that neuron is a linear function of x. But if we add on the invariant that no don't care neuron feeds into an on or off neuron, then we get that for all neurons that are on and all neurons that are off, the output of those neurons is linear. So therefore, the set of points that satisfy this activation pattern is a convex set. We use the set defined by this activation pattern as follows. Suppose we are given a property P and exactly one input point that satisfies this property. We'll now look at the activation pattern that corresponds to this point, this one particular point. So in this activation pattern, each neuron will either be labeled on or off, but we will not have any don't cares because we are given a particular input. Then we check that given this activation pattern, we check if each point that satisfies it also satisfies P. If it doesn't, then the procedure terminates and we simply return an intersection of the points that satisfy this property with the activation pattern. But if every point in this activation pattern satisfies P, we try to add don't cares to this activation pattern and try to capture a larger convex region. So what we'll do is the function find minimal, it takes in an activation pattern and a property, and it tries to add don't cares to neurons and keep on repeating this check if the activation pattern still satisfies P. Note that this is done in a way that satisfies the invariant that no don't care neuron feeds into another neuron that is on or off.
We just saw one approach to the problem at hand, which is finding regions in the input space that guarantee a certain property P on the output space. The issue with this approach is that the property P that we're trying to verify is a high-level specification, which concerns itself only with the outputs of the network. And we're in this approach, we're directly trying to relate the architecture of the network in terms of its activation patterns to the property P, and there is no general intuitive connection between the two. And this intuition is backed by our experiments. In our experiments, about 40% of the cases stopped at no, which means that this procedure that we just saw does not even go to the find minimal phase where it could, minimalize the activation pattern to find a relaxed region in the input space. Now we introduced the motivation for our methodology. What we are trying to do is, instead of the property P, we try to run the same procedure but with the property I. And this property I depends on both X and Y, and it is designed in such a way that it acts kind of as a bridge between the low level details or architecture of the network and the high level property P that we want to verify. So what we'll do is the same thing. We'll call the find minimal procedure, but not with property P, instead with property I, in the hope that we get more don't cares, and in turn a more relaxed activation pattern, and in turn a larger region in the input space. The constraint on this property I is that the property P that we want to verify should be checkable using I. This will be made more clear in the next slide. So consider the property P, which is class dominance, that the logit for class 0 is more than the logit for class 1, which guarantees that the output of the network will be class 0. For this particular property P, we want to design an intermediate property I, which will help us capture a larger region in the input space. So let W be the weight vector such that inside the initial activation pattern sigma with which we start the procedure, the output of the network Y is a linear function of X. So Y is Wx. Now, based on this W, we will create an intermediate property I1 of X and Y as follows. So this says that the difference in logits of Y0 and Y1 is exactly equal to the difference specified by the weight vector W. Note that for all inputs X that lie inside the initial activation pattern sigma, the formula sigma X implies the intermediate property I1 XY. So the yes branch will always be taken. So here itself we can see that this is an advantage that we provide in our method over the baseline approach. And remember that it should be easy to check PY using the intermediate property I. So that is also true, because if we find the minimal activation pattern sigma prime, so the formula sigma prime X, if it implies I1 XY, which will be the case uh, as a result of the find minimal procedure, then it means that sigma prime X, when intersected with the hyperplane W0 minus W1 times X greater than 0, this entire thing will imply PY. So essentially the property P is checkable using the intermediate property I1. Now this was just an illustration. This choice of property I1 is a little naive, because what we want patterns also into our relaxed activation pattern in the find minimal call. And actually W0 minus W1 is likely to change outside the initial activation pattern. So it's not, I mean, we will take the yes branch in the procedure, but we will not go very far in terms of relaxing the activation pattern. But with this intuition, we can design another I. So this is the same thing. The I1 was too stringent because of this particular equality. But using this intuition, we can design another intermediate property I2, which is an inequality, and it's sort of a relaxed version of the first one. So I2 is designed as given here, and it simply says that for a parameter epsilon, which has to be greater than 0, this intermediate property says that the difference in logits subtracted from the difference in the weight vector should be greater than negative epsilon. So again, we can check py using this intermediate property I2xy, because if we get the relaxed activation pattern sigma prime, which implies I2, then it also means that sigma prime, when intersected with this hyperplane W0 minus W1x greater than equal to epsilon, this will imply the property py. So again, py is checkable using I2, and this seems like a reasonable choice of the intermediate property, because this holds for any parameter epsilon, and then we can um, run the procedure for multiple epsilon and see in which case we find the largest region.
Hi, so I will start with an illustration of our approach and followed by some experimentation and then the direction of future works and the conclusion. So starting with an illustration. So we took a toy network which had like 4 hidden neurons, and it has like 2 input dimension and 2 output dimension, and let's say the output are y0 and y1, and we plotted the activation pattern for different input points, and we can observe the convex regions as for different activation patterns, which are like honeycomb structures. Then we have a property line which signifies the decision boundary between y0 and y1. So for all these input points, y0 is greater than y1. For these particular points, y1 is greater than y0. And then we start with for our approach, we start with an initial point denoted by this red cross, and we first of all relax our property to an interpolant I, and for that interpolant I, which is an epsilon relaxation of the property, we try to minimize the activation pattern, and we are able to reduce 3 out of 4 of the constraints from the activation pattern uh, of our hidden network and for our hidden neurons, and we are able to reduce 3 out of 4 of them. And but like this is for the interpolant I. Actually we want to verify the property P, therefore we have to move from I to P and add an additional constraint which we call as our critical line, and is denoted by this red line. And so the overall region that we output is the combination of the activation constraint and the critical line, and this is the region that we will output. And we will say that for all these points we are able to formally say that y0 is greater than y1. So now let's compare our approach to baseline, or the paper mentioned earlier. What they do is like they start with an initial point, and they directly, without like using interpolants, they directly try to reduce the activation pattern. But because their property is more stringent, they are not able to reduce many neurons to don't care, and therefore they have like 2 constraints coming out of the activation pattern, which is denoted by these 2 black lines. And so the final region they output is smaller as compared to what we can output using the interpolant I. So this clearly shows that where our approach can be beneficial as compared to those. Moving on to more practical setting where we take a real world data set. So first of all, we are free to choose any classification data set, just because like we are verifying a class dominance property, or a property which says when class 1 will be output rather than class 2. Therefore we don't care what data set we are considering. And for like simplicity and easiness of interpretation, we took a diabetes data set which has like 768 different observations, 10 or 9 or 10 features, and we can like train a simple neural network which is able to achieve 82% accuracy on this particular data set. And so on this particular data set, to compare the results empirically, first of all, how do we compare convex regions? So because the output of our algorithm as well as baseline is convex regions in the input space for which the property P holds, therefore there is no direct way to compare them. And so so there are 2 defined metrics for this particular comparison. One measures the size of the convex region. To measure the size of the convex region, what we do is like inside the convex region we try to fit and largest volume box and compute its volume. So the larger the box we have inside the convex region, the more the size of the convex region. And also like note that in addition to the size of the convex region, we are also interested to know how important or how good that convex region is. So we want to identify those convex regions which have high probability mass in the input space. And so to a proxy for that would be to find the number of training points that lie in that particular convex region, and which we call as our support metric. So these are the two metrics that we will be considering. And so moving on to how do we choose epsilon for our experiments, and what's the intuitive and empirical evaluation of our choice of epsilon. And so note that epsilon is something that takes us from property P to property or interpolant I, which helps us to minimize our activation patterns. And so note that if we increase our epsilon, we will be able to relax more neurons who don't care, and therefore we have lesser constraint from the activation pattern point of view. Therefore, increasing epsilon seems to be a good thing. But there's a catch. Like if you increase epsilon too much, then the critical line or the line that we have to add, because we have to move back from interpolant I to property P, would be more and more stringent, and therefore therefore there exists a natural trade-off in choice of epsilon. And we are able to experimentally verify this particular trend in both the metrics on our data set. If we try to measure for different epsilons what's the value of the metric, we see that there is first an increase and then there is a decrease, and therefore a best value or the sweet point lies in between. So moving on to the results that we have on the diabetes data set. First of all, let me explain you the experimental settings. So there are 768 different input points. In those 768 different input points, 127 different activation patterns are realized. And for all of these activation patterns as the initial activation pattern, we run the experiment for our approach as well as the baseline, and try to compare the metric values for all these points. Note that we obviously want two things. First one is we want to perform better in the metric value, that is lie well above the baseline. And the second thing is that we want to be more robust to the choice of initial point. Therefore, for all the input points, we want to lie above the baseline. So yeah, so the goal is both to like improve the metric values as well as be more robust. And as we can see that we are able to achieve these goals, because for most of the points, blue points lie above the red points. So for the plot on the left, the logic factor is fixed, or the epsilon is fixed, while for the plot on the right, we for each input point we choose the best logic factor or epsilon for that particular point. Therefore, our results are increased significantly when we have like this leeway to choose our best epsilon. And as we can see that this is kind of expected, because what baseline does is has a very strict control on the property, while we have like a band of epsilons for which we are choosing the best one out of it. So that's why we out to lie above them as well as like across different points for this particular thing. And these are the results on the support metric, but the results remain the same when we move to log volume metric. And again, we are able to find points where we are performing much better than the baseline, and we are able to identify larger input regions. And like this result, again, these are compounded very much if we do choose the best epsilon for our experiments or for our approach. So to conclude the results, we have like we are able to perform in 71% of the cases better than the baseline. This means like out of 127 different input points, in 71% of those, our metric values were better than the baseline. And we are like more robust to the choice of initialization of the activation pattern by the very nature of the approach, because we do epsilon relaxation of the property. Therefore, we are guaranteed to call minimalize activation pattern call, and while no such thing exists in the baseline, so they are only able to reduce activation patterns or neurons to don't cares in 53 out of 127 cases, while we do it in all the 127 cases. So clearly we are more robust in theory to the initialization point than the baseline. And so to moving on to like the theory of linear interpolant is like fairly general and it is sound, and we have given like enough prototypical evidence to merit more research in this direction. So we have chosen smaller data sets and networks, but definitely a possible extension is to like try out different complex data sets, complex networks with multiple layers, try with MNIST and compare our results with the baseline. And next thing that we want is that because we are defined this property for the property of class dominance, or where y naught is greater than y1, uh, but like nothing restricts us to try out different other properties which might be very safety critical in different scenarios, and we want to like devise theory for those particular properties as well. So that is another direction of future work. And another thing that intrigues us is that because of new advanced architectures which use like convolution, max pooling, can we extend our approach to these particular operations as well? So that is an important question that we want to answer. How does these convolution or max pooling layers impact the theory about activation patterns and like solving doing the property inference? And again, we have restricted our approach to in this particular talk to ReLU networks, and but like because of other non-linearities like TANH, things can get complicated. The activation patterns would no longer be linear, but it would be interesting to know how can we essentially verify those particular networks as well, and that is something that we want to try out as a possible direction of our future work. So with this, I think I will conclude this talk, and hope you liked it. And like, if you have any questions or any doubts, like feel free to reach out to us. Thank you so much.